Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk, or in this video I want to talk about band character and partial densities of states. What we have seen in the early lectures where we discussed the free electron model, where we had basically plane waves as our basis states, is that we can calculate from those the conductivity by looking at the Fermi function and see how much this shifts. And there are many other experimental observations that we can calculate based on the wave functions and Fermi theory. We then noticed that when you have a periodic potential, the plane waves are no longer eigenstates. We get Bloch waves out of which we can construct the eigenstates. Eigenstates are Bloch waves. And with those we then can also calculate the electronic properties. Now, when you measure the conductivity of a system, then very often this is not enough to really describe the experiment. For some reason that we will discuss today, which has to do with the character of the wave functions, you do not measure the full conductivity, but because of the orbitals that are involved in the atomic structure, you only connect to a part of the system. And let's make an example. We can look at a one-dimensional chain of carbon atoms. Of course, if you would do a real experiment, this could, for example, be a graphene sheet, but let's just work in one dimension for our chain here to make things a bit simpler in the example. And we define our coordinate system, y out of the plane, x in the vertical direction and z in the horizontal direction, such that we have a one-dimensional chain. And we have here carbon atoms. And as a basis, we take the p orbitals. Well, we have seen before that we then can calculate the band structure. Minus pi over a to pi over a, crystal momentum 0. And we have as a basis the px and py orbitals, which are perpendicular to the chain and make pi bonds. And we have the pz orbital, which is in the plane and makes a sigma bond. So px py has a bond like this, and pz has a bond like this. Well, we have seen that the hopping matrix elements for two exponentially decaying wave functions that are both positive is negative. Here we have two lobes that are pointing in a direction towards each other. The angular momentum gives you the same phase, so the hopping for the px and py orbitals is negative. For the pz orbital, there is an additional phase that comes into your wave function due to the angular part of the wave function. One lobe is positive, one lobe is negative, and therefore we have the pp sigma hopping to be larger than 0, whereas the pp pi hopping is smaller than 0. So we find the bands for px and py to be equal to the s bands with a negative hopping, therefore a minimum at k equals 0. Whereas when we look at the hopping from the pz orbital, then the matrix elements changes sign, and therefore this is a positive hopping matrix element. Well, if you put your Fermi energy in there somewhere, you can then calculate the velocities of the band. The velocity of the pz orbital will be larger than for the px and py orbital, so the conductivity in the pz orbital will be larger from the px and py orbital. And you can calculate then what the conductance is based on those, and you will find that the resistivity coming most, or the conductance mostly will come from the pz orbital and much less from the px and the py. Of course, depending on your Fermi energy is, you could even have that you only cross one band and not the others, and then it will be only that orbital that contributes to the conductivity. Well, in a one-dimensional chain there is no interaction between them, and then depending of course on the crystal structure there might be interaction between them. Now, when you want to make a measurement of the conductance of such a system, you have to put a connection to it. So let's take two atomic tips and let's make them out of gold atoms and connect to your one-dimensional chain. And we do this on the other side as well. And then we can measure the conductivity. For our gold atoms, the states at the Fermi energy are made out of s orbitals, so we can take a basis of s orbitals. If we now look at how we connect to our gold orbital, then we can either have an interaction where we have locally an s orbital and we hop to the px orbital, which has an sp sigma matrix element of hopping, or we have an s orbital and we hop to the py orbital, or we have an s orbital at the gold and we hop to the pz orbital, which is in the direction of the one-dimensional chain. Now for this case we should realize that you have a symmetry in space. This has a positive sign, so on the left you have something positive times negative for the wave function, on the right you have something positive times positive. So these contributions to your hopping matrix elements are minus t and plus t, and integrated over whole space this is exactly 0. And the same is true for the pz orbital or the py orbital, but now in the y instead of the z direction. So here there is no hopping. So an electron coming from the gold, traveling to the carbon atoms, going back to the gold, cannot hop into the pz or the py orbital, but only into the px orbital. So in an experiment like this, you do not see the conductivity of the entire system, but you only see the conductivity through the px orbitals, which of course is a huge change because the pz orbital has the smaller conductivity, or if you put your Fermi energy at a place where the px and the py are perfectly filled, you have a metal, but nonetheless you see no conductivity in an experiment like this, for the very simple reason that you do not couple to the right states at this point. So we're not only interested in what the energy of our eigenstates are, we also need to know what the character is, which atomic orbitals build up these wave functions, because that is what you couple through when you do an experiment. And these kind of couplings are often called matrix elements, and in order to calculate those matrix elements we want to know what the band character is. So for the band character we have a set of local Bloch waves, or Bloch waves, not local Bloch waves that are built up out of local functions. And these local functions can be your atomic-like s, p and d orbitals. And then we have band eigenstates. Phi, k, tau, which are linear combinations of your basis orbitals. The band character is now defined as the overlap between the eigenstate and the basis function. How much of each basis function contributes to the eigenstate. And in our example of a one-dimensional chain with p orbitals, because there is no interaction between the px, py or pz orbital, these bands are of pure px or py character, and this band is of pure pz character. But when there is an interaction between them, you will see that your band eigenstates become of mixed orbital character. Instead of looking at the bands, we can also look at the densities of states and then the partial densities of states. Which tells you how much each basis states contribute to the total density of states. So the partial densities of states of quantum number tau at energy omega is a sum over all crystal momenta and all eigenstates or band indices of the band character of that eigenstate times a delta function at the eigenenergy of that state. Where epsilon k is the eigenenergy of the state with wave function of crystal momentum k and band index tau, or tau prime in this case. And this we then can use to determine, for example, what the conductivity would be in the previous example. But for many more experiments, it is important to know what the character is. There are two very important properties of the partial densities of states that I would like to discuss, and we can express those in the zeroth and the first moment of the partial densities of state. So let's just first have a look at the zeroth moment of the partial loss. And the zeroth moment is nothing more than the integral of the densities of states, or the partial densities of states, over energy. Now we can now put in the definition of the partial densities of states, a sum over all crystal momenta over all band indices of the character of your eigenstates times a delta function omega minus the eigenenergy of that state integrated over frequency. Well, the integral over a delta function is just 1. There's no energy dependence in the previous part. So what is left is a sum over all crystal momenta, the band index, the character we project to of the band character of that state. We can write out the definition of the character, which is the sum over all crystal momenta and the band index on the Wannier function we project to, and the eigenstate we have norm squared. Well, we can write out this norm squared, where we have our wave function k tau, and then a sum over all crystal momenta in tau, phi k tau prime, phi k tau prime, and our wave function to which we projected omega k tau. And this is 1, so what is left over is omega k tau, omega k tau, and that is exactly 1. So the integral over our partial densities of states is equal to 1. We start with one state to which we project, and that state can change in energy, but you will never get more or less than just one state that we have. So each basis function contributes to all eigenfunctions in such a way that if you sum up all eigenfunctions and look how much the contribution on that state is, that is in the end exactly 1. There is a conservation of the number of quantum states in quantum mechanics. If I have a Hilbert space with a basis of n basis functions, then you will find n eigenfunctions in that system. The second is the first moment of the partial DOS. And we now integrate minus infinite to infinite, and the energy times the densities of states at that energy. And this is the integral minus infinite to infinite omega, and we fill in the definition again. A sum over all wave vectors tau prime chi t wave vector tau prime delta omega minus epsilon k tau prime d omega. In order to work this out, we again write out what the band character is. We first can do the integral over the delta function, of course, but now it's a delta function multiplied with omega. So the integral over a function of omega times a delta function of omega minus epsilon is the function evaluated at epsilon. So what we have here is the sum over all crystal momenta, and band indices tau times the character projected to tau of that state times epsilon k tau prime. So times the energy that we have. And now we write out the definition of the band character, which we have here. K tau prime omega k tau, and then the eigenstate k tau prime times the eigenstate energy, which is, we can write out that square k tau, the eigenfunction tau prime, epsilon k tau prime, the eigenfunction k tau prime, omega k tau. We here have a sum over crystal momenta, but there is a crystal momenta also in the Wannier functions. So let's transform our Wannier functions to real space. We do that for the left and for the right. And then we have the sum over the crystal momenta in tau prime. That's 1 over v e to the I k dot r minus r prime for the Fourier transform on the right and on the left for the bra and the cat. And then we have omega r tau psi k tau prime epsilon k tau prime psi k tau prime omega r tau. Well, what we have here is a sum over all crystal momenta of the difference between two vectors. This is an oscillating function when r is different from r prime. When r is equal to r prime, this is 1. So there's a delta r prime in there, and then there's a sum over r prime of 1 over v, which makes 1 again. So this double sum over r prime is just with this 1 over v times e to the ikr, making a delta function between r and r prime, such that we are left with the sum over crystal momentum and band index tau of our Warnier function centered at r tau phi k tau prime epsilon k tau prime, the eigenstate k tau, and our Warnier function centered at r tau. And this integral is independent of r. Well, here we have a sum over k, and now we have a projection to the eigenstates, which forms a full basis, and epsilon k. So what we have in here is nothing more than the Hamiltonian. So what we have here is the Warnier function, local, the Hamiltonian, omega r tau. And this is nothing else than the on-site energy of our Warnier function. So we see that the first moment of the partial densities of states is given by the on-site energy of the orbital to which we project. So if you start with a certain orbital, have it interact with other states, then the energy will go up and the energy will go down, and you get some admixture of your two states in such a way that the first moment is exactly equal to the on-site energy where you start for both of these states. So the amount that you go up here is directly related to the amount of admixture that you get. And this is not only true for two orbitals, but this is true for many orbitals as well, such that the first moment of the densities of states is equal to the on-site energy. Or in other words, interaction of a system with its neighbors is not going to change the local energy that you have, but it's of course going to change the energies of the eigenstates that we have. So in the next videos I want to look at a few examples of real materials where we can have a look at the tight binding properties, the band characters, the local densities of states, as well as what the Warnier functions look like, and see how free electron bands and tight binding bands combine with each other in different cases and different materials. For now, thank you very much for your attention. We see each other in the next video. Stay healthy.